Hello and welcome back to the channel. It's Mark from Powersonic and Apprentice 121. Today we're going to have a look at an EICR on a very simple installation, a couple of circuits. We're going to run through it. We've got a ring vinyl circuit, a lighting radial circuit. Be interesting to see what values we get, compare them both live and dead, and show how they get inputted into an electrical installation condition report. 'Cause I know some of the learners following along have been asking recently how you fill those forms in. So I thought we'd have a look at it. We'll open electrical OM, we'll go through the EICR, let's get straight to it. Let's have a look around the accommodation and see exactly what we're faced with. That's the first thing I recommend anyone would do when they're performing an EICR. You need to have a good look around and see exactly what you are fronted with. And first and foremost is the consumer unit. You can see up here we have a main switch, and then we've got a couple of circuits unlabelled. We've got a B32 and a B6. So I strongly suspect that they are going to be the power and lighting, probably a ring final circuit, and a radial lighting circuit. Now there is also a fire detection system in here that will most likely be supplied from elsewhere, and we need to make sure we note that in the limitations of our inspection that it's not forming part of our report. Fire alarms are mentioned in BS 7671, and although there are a separate British standard for that particular type of equipment and installation, it's well worth making sure you cover that off in your limitations or your outset of what the EICR is covering, that is excluded. We're not going to be covering that in this aspect of our report. There is also an emergency light above the exit point to this accommodation, and we will be testing the fixed wiring up to that, but obviously we're not carrying out, I say obviously, I'm not carrying out emergency light testing during the course of this inspection, so we won't be duration testing it, but we will be making sure it's got an adequate and safe supply. So again, documenting that in the certificate is super important to make sure you're stating clearly what you are actually covering. First observation would be that we've got a plastic enclosure on the consumer unit. It is pretty close to the point of exit, and this is accommodation that people would pay to come and stay in, so kind of Airbnb hotel type arrangement. So there's that consideration if it's a factor, and then basically just wandering around and seeing what accessories we've got. So we'll count up the sockets first and foremost. We've got one pretty much close to the consumer unit. There's another one over near this desk area. We've got one near the tea and coffee making facilities. Nothing lower down on that. We're checking the cupboards to see if there's any power points. There's nothing inside there. And I don't expect there'll be one up here either. Nope, so there's nothing in those cupboards, which is good. And we can see we've got some lamps over here. So we'll follow the wires and see where they may be plugged in. So we lost the focus there. Apologies about that. Should have come back into focus now. We can have a look behind here and see what we've got in terms of the lamps. So this one is on a 6 amp plug top. You can see that into there. And the other one is also on a 6 amp plug top, which is just behind the bed there. We've got a socket for the TV, so I've got another one there. So that's 3 double sockets, a couple of 6 amp outlets for the lighting. Just double check that one at this side. Yes, it is. It's just down there. I don't expect we'll have any sockets in the bathroom, but they might have gone all European on us, so we'll have a quick check. Nothing in terms of a socket outlet in here. The only electrical equipment we have in the bathroom is the fan, the main light, and this light above the mirror. So there's no other electrics in there. So pretty straightforward on the power front. 3 sockets, a couple of lighting outlets. We'll see if the lighting sockets are off the lighting or the power circuit. Be interesting to see on that one. And yeah, that's that. Actually, it's what we got. 1, 2, 3, 4. So 4 lighting sockets, 4 power points. So we need to get that into our certificate. In terms of the lights, we'll look at the switching points first. So we've got one near the door as you come in. You can see one close to the bed there, and one outside the bathroom door. So there's just 3 points in terms of light switches. Light fittings themselves, we've got the emergency light above the door. We've got one just above the entrance. So that's 2. Got one above the bed. That's 3. One in the bathroom is 4. The one above the mirror is 5. Extractor fan, call that 6 points. I expect that will be on that circuit. So now first up, if we pop the power, while things are on and functioning, a really simple way of checking what is exactly on what circuit. Actually, before we do that, I'll just make sure all of the lights and lamps are on. be a good place to start. That's one of them popped on. Let's stick this one on. And we've got everything else on and working. It's just a really quick visual way of identifying what's doing what without getting any test instruments out. We've popped the power off on what I suspect to be the lighting circuit. We can see that emergency light's activated, so that's seeing that. We can see this has gone off. The bedside lamps have gone off. This lamp that's plugged into the socket outlet has remained on, which is useful. We've lost all the power in the bathroom. Lamps are off, lights off, fans off. So that's a good indicator to us that all of the lighting points, including those 6 amp outlets just down behind the bed, are all wired off the lighting circuit. So happy days. Can pop the power back on for that for the moment. And then with the power points, again, we knock the power off. You can see it's taken out that lamp. The rest of the equipment's all remained on. TV's lost its power, and we'll determine the rest of that with our dead tests. So the next stage would really be to carry out some safe isolation, so we can isolate this board leading up to it. I can't show you that 'cause it's in a public area of this premises, so I'm going to go and do that now. We'll get that locked off, and then we'll come back to this board, open it up, and see what we've got inside it. So I now need to get a measurement of ZdB for this little consumer unit, and I'm doing that with the camera down, so I'm nice and safe. I'm onto the earth bar already. I need to attach the probe onto the line, as you can see here with the MFT Pro Plus. So we can do that, and then we'll see what value we get. I'll jump back and show you rather than trying to hold the camera with that board open. So I'm going to put a bit of PPE on, I'll take that measurement, and we'll jump back and have a look at what we get. So you can see I got a value of 0.43 on the live and protective earth. Now that was consistent with doing the test on a no trip setting, but I've popped it onto the RCD equivalent to see if there was any difference, and there wasn't. But interestingly, we've got 0.53 on our line and neutral, and if we think about it, we've got an extra 4 mil on the supply cable coming down here for the earth in the LSF twin and earth, and we've also got that 6 mil earth coming along as well down to here. So there's some extra conductors in there, and it is also a TNS supply. Now whether it actually is, based on the IET's advice to assume everything is TNTS now, kind of explains that difference. We've got the parallel paths with the bonds to gas and water as well, bringing that LPE loop down. But at least we know at this board we've got 0.73 as our ZdB, and it's important to remember when you're doing your ZdB that you do that with your parallel paths in place for your earths. When you were doing a ZE at the main point of the distribution board, you would disconnect the earthing conductor, but in this case, because it's a ZdB, basically a ZS at a consumer unit or a distribution board that's remote from the intake, on like your first distribution board if you like, then you need to make sure you do that with those parallel paths in place, and we call it ZdB. So we've got the power off now, and you can see inside that consumer unit my suspicions were correct. We've got a 10 mil radial circuit feeding down to this board. That is on a B50 breaker up front, so there is going to be an issue of selectivity between that B50 and this B32 in that board, but it is what it is. When you are staging MCBs, there will always be that overlap. And then you can see we've got our ring final circuit onto the power through this room, and we've also got the lighting, which appears to be on a 1 mil, running off around the room as well. Counting up the earthing conductors inside the consumer unit, I can see we've got them all present and correct. So we've got our main earth coming in, we've got the earths for the ring final circuit, we've got the earths for the lighting, and what appears to be a separate earth running in as well to get us some steps and have a look at that and see exactly what we're faced with inside there. And all the neutral and line conductors are present as well. So that's a great start. We can now have a look at carrying out some continuity testing. So that's what we start with, continuity testing of our CPCs and protective conductors, and then we can move on from there. So you can see I've carefully positioned the TIS MFT Pro on top of this coat hook, and I just need to zero these leads off to start with. So if I press on the zeroing button, it should carry out a zeroing check. If you can see that coming up on the camera, and it's done that now, so we know our leads are good. We can go back to the main screen. And then the first thing we need to do with the ring final, if I get these croc clips apart, Just bear with me. So the first thing I need to do is get some end-to-end resistance readings on the line, CPC and neutral of this ring final circuit. So we'll do the CPCs first, and of course the installation electricians had put them in the same sleeving just to make things lots of fun. So you can see they're not touching in the back there, to make sure you do keep them separate. And then we're going to carry out that test, and that'll give us our end-to-end on the CPC and get that to come into shot for you. Going a little bit closer, and you can see that that is 0.56. That's focusing in for you, 0.56 ohms on the CPC. And this is 2.5 mil, 1.5. So if we come back to these now, and we get our lines in on the croc clips again, you can see that. So we're on to the end of the lines, and we can go back to the meter, and there is a calculation that you can do with this. So this would be 1.67 times less than the CPC value. So if you were to take this value, for example, multiply it by 1.67, it should be reasonably close to the CPC. We've got 0.33, so just need to get the neutrals out now. They're still in this little bar here, and we can get the end-to-end resistance values on those as well. So you can see we're croc clipped onto the neutrals now. We'll come back to the test instrument. We can save that value. Hit test again, so you can get this to focus, and we've got 0.35. So roughly speaking the same. There'll always be a little difference due to the terminations in the back of the socket fronts, and also the potential length of the cables in the consumer unit, and the socket fronts will always play a part. Bit of contact resistance as well in the connectors, so they're never going to match up totally, but you need to remember that's a very small difference. I'm happy enough with that, I'm not going to worry about it. So that's our RN end to end. So you can see I've shorted out the line of one leg with the CPC on another, and vice versa. So essentially you've formed a big loop through the line and CPCs. Got this socket front off down here because we're doing some internal inspections as well. And I've gone onto the line and CPC terminals direct on the back of the socket. If I now hit the test button, it'll carry out a measurement. And if you see there, if I can get it to focus again, we've got 0.22 ohms. The camera's really working hard here because I'm kind of working one-handed, so apologies about that. You can see as it comes into focus, that is 0.22 ohms. And there is a calculation we can do with that, and we'll speak about that when we get to having a look at the test sheet. So you can see in the back of the socket there, it is reasonably well dressed, which is a good sign. So that's something you need to do, is open up the accessories. We're going to open up some of the light switches and light fittings as well, some of the other sockets. Make sure the terminations are all in good order and there's nothing looking out of place. The best form of approaching an EICR is using your eyes and having a good poke around, especially in a small little setup like this. Now obviously if they're tiled in or there's some nice wallpaper and paint and you're not too happy about removing it through the prospect of causing any damage, then you need to note that in the limitations section as well, and make sure you agree it with the client. They may say it's fine and that you can pop the socket off and not to worry about it, but we've all been there where there's damage to wall surfaces and people start complaining after the fact, so make sure you have those conversations. And yeah, we've got the 0.22 ohms for the R1, R2, and that's been repeated around the other sockets. I demonstrated this one off the back of the socket, but of course you can just use a plug-in adapter, get the same value. I've shown that loads on the channel before, and then you can see any impedance that may be coming through the actual pins on the socket itself. This is just another way you can go about doing it when you're just testing off the wiring. So say for example, you've done your R1, R2 around all the socket circuits, and one in particular was presenting a higher value. You could open it up because you'd need to see if there was a problem with the terminations anyway, and see if they were okay, take a measurement, and then you know with pretty high confidence that the issue is with the accessory itself. Now obviously again, as I've shown on the channel before, if this was initial verification, you would do this anyway to verify your neutral conductor, but you'd make the same crossovers with the neutral and the line or the neutral and the CPC and get a value. I'm going to do that, just make sure we have got continuity around everything and that it pings out as normal. It's a good way of identifying any spares and see if there's any problem there. So I'm going to run around and do that, and then we'll move on to having a look at the R1, R2 on the lighting circuit. So I've linked out the line and CPC for this lighting circuit. I've been and dropped a few of the accessories and had a look around, and as suspected, the end point is in this bathroom. Line and neutral comes into this light fitting here. The light above the mirror doesn't have an earth, it's just a class 2, they've just taken line and neutral to it. We then feed back to this isolator on the bathroom fan, and then it comes over to the fan itself. Little tip, when you're opening things with stuff underneath, close the toilet lid, plugs in the sinks, make sure you're not losing any of the little screws like these ones down there, because you'll regret it and you don't want to be fishing them out from a drain or a toilet. Now the CPC has been brought into this fan, but it's not terminated because it, again, class 2 item, so there's no need to earth it, but it's in there, so there should be earth continuity to it. If I probe onto, we'll go for the line first up and hit the test button. So I just had to get some replacement batteries in, and you can see on the actual red, so the line, that's the permanent line coming into this fan, we've got 0.51. I will just pop it onto the switch line, yellow, hit the test button, see if we get any different. So that's a little bit higher because it's running through that switch leg, as you would expect, so it's not coming straight to the fan on the same path, so we've got a bit of a difference there. So that is our R1, R2 for the end point on this lighting circuit. That would be 0.67. So we've got our continuity of protective conductors now, and we can have a look at doing the next stage of testing. Okay, so we can do some insulation resistance testing. Now, there is a few things that will affect the values that I'm aware of. Obviously, all the lamps are in, all the light fittings. There's that light fitting in the bathroom, which I'm not going to be disconnecting out of circuit. There's also the extractor fan. There's the lamps that are in over there as well. And we've also got a USB socket. So there are a few things that are going to affect the values. Now, we could approach this as a global IR value and see exactly what we get. And if it reaches above 2 megohms, then we're all good in theory. However, this has been a smaller installation. I thought it'd be interesting just to break it down. So I'm going to separate this out. We'll do it at 250 volts first. I always recommend you start there. And you need to remember, with this being an EICR and not initial verification, you take the level of testing to where you see fit as the inspector based on your visual assessment and how you see the results you're observing. So if you are all clear at 250 volts, it's a small install and you're happy, you can leave it at that should you wish, as long as you note the tests you've taken and the reasons why you've taken them. You'll note here I've popped the neutral out for the lighting circuit. Now that is because essentially the line would run through all of those lights, return back through the neutral. If you leave it connected in there with the socket line, the same principle happens and those two circuits end up connected together. So we want all of our earths in, all the CPCs are in together. Parallel paths, there is a single earthing conductor running back to the distribution board that supplies this alongside the 10mm LSF that feeds down here. All of these circuits are in LSF, by the way, just to mention. So if we go onto the sockets now, we can see we've got a probe onto the earth bar, go onto our socket circuit, and note that the MCBs are in the off position, so this isn't a global test. Like I say, we've popped that neutral out. So this is just testing the line path to earth on the socket circuit, and you can see there it has measured off the scale. So that USB socket doesn't appear to be affecting things on that front. If we jump onto the neutral bar now, so the same test on the socket circuit, but this time neutral to earth, hit the test button. Apologies for the poor camera work, this is difficult when you're up here on there. And again, we're measuring off the scale, which is what we would kind of expect to see. That'll focus, happy days. And again, then you can do between your live conductors in this case. So I'll pop this over onto the neutral bar. Because we've unplugged everything, I've been round to unplug the TV, all the other sockets are unplugged, so there's nothing in circuit. If I probe onto the line again of this socket circuit and hit test, I would expect this to be very low, and we can see it's giving us a dead short. Now we can go to the lighting circuit, and as I said, we've got the emergency light, there's other bits and pieces. I would expect there'd be some sort of electronics causing us some kind of issue on that front. Before we do that test, I'll just cancel that because I need to drop it down to 250 volts again. So do that. We go onto the line, hit test. As you can see, I'm on the line of the lighting circuit now. We're on the earth bar again, and you can see we're measuring a value this time. It's around 23 megohms. So that's a bit different on the lighting circuit. It's still above our 2 megohm value, and again that'll be due to electronics that are in the fan that are potentially in that light in the bathroom, and also the emergency light as well. So with this one, we have to crop clip onto the neutral lead because I've popped it outside that bar. And again, onto earth, hit test, and we should get a similar value, and we are. So it's reading around 22, 23 mega ohm as it was with the line to earth, which is great. And then we can just do a line to neutral. And again, with all the lights in circuit, I would expect this to be very low, and we can see it's giving us a dead short because all the lamps are in place. That's sort of what you'd expect to see. Now, I'm not going to ramp that up to 500 volts because I am aware of the electronics in circuit. I don't want to cause an issue. We're above our 2 mega ohms, so I'm happy with that and an understanding of why those results are presenting in the way that they are. So that's our insulation resistance testing on the socket circuit and on the lighting circuit. And just to prove a point of concept, I'll pop this neutral back into the neutral bar and we'll measure the socket circuit again, and I'll show you what I meant at the start of all this. Seeing is sometimes believing. So same test, we're on the earth bar there. If I probe onto the line connection for this socket circuit, all I've done is pop the light in neutral back into the neutral bar. If I hit test, in theory I'd expect to see this come out at around 20 mega ohm as well, which it is doing, if that'll focus. So you can see that's dropped the socket circuit off, if it will focus, to 23 mega ohm as we got on the lighting circuit, and that's finding the same path through that neutral connection in the neutral bar. So although we've got the lines isolated, we have still essentially got those neutrals tied together. So there's a path there. When you're doing your insulation resistance testing on a circuit by circuit basis, it's important that you understand where those parallel connections can be. Obviously with the CPCs and your parallel paths on the earthing, they kind of have to remain, but you need to remember to separate apart your line and neutrals if you want to get a true value of insulation resistance on those circuits. So for the eagle-eyed among you may have noticed that I popped the ring vinyl into the wrong MCB when I've been popping them back away to the lighting, and that's a firm example of why you need to double and triple check everything you're doing, because that's a simple mistake when you're deconstructing a system that you can make if you're not careful, especially in a busy board. So if you're taking terminations out, you're putting jumping leads in, before you're re-energizing the board, double and triple check everything you've done and interfered with visually so that you're happy it's hunky-dory to then reconnect and energize to do some of the live testing. And that was noted by me. Simple mistake to make, just rushing around putting terminations back in the wrong order, especially when you're a dyslexic old fool like me. And that's why I have processes in place to check myself once and twice and a third time. And we can put this all back together now, get energized and see what ZS values we've got on these circuits and how they compare to our dead tests. So with our socket adapter just into that socket circuit below the distribution board, you can see we've got a live PE value of 0.66. I repeated it on the no trip. It's consistent if it is or it isn't. And again 0.72 on the line and neutral. So it's a little bit above what we measured in terms of our ZdB. We'll have a look how all that plays together with the dead test measurements, the live test measurements, and how some of that might affect those values and cross over some of the measurements we might be making. There's no RCD testing to do on this. The lighting circuit, should you wish, you can go and take a ZS measurement at the end of the circuit. It's perfectly acceptable, as lots of people have made the point before in terms of guidance note 3 and the wiring regs, that if you want, you can use the calculated method of using your ZdB and your R1, R2 to determine what your ZS is. Obviously, if you're opening that fan up, there's live terminals at play. It's not as easy to get that measurement as it is just using a socket adapter into a socket front. However, I've got the TIS light mates, so I'm going to pop them into the local light point and we'll see how that value compares to the fan. Having taken a measurement between the line supply to the fan, it should be consistent-ish with what we would get at that point as well. So just a bit of extra information. I'm not going to open the fan back up with it live and then try and take a measurement in there as well. I don't see the value in doing that at this stage, so we'll move along, see how all this comes up and input the data into a test certificate.
So I thought we would have a little look through recording, filling out of a test sheet, because there's been a few learners and trainees who've asked me specifically about that. We're not going to cover in all of the basic stuff, so addresses and such, but we'll focus in on some of that test data, and I'm going to use electrical OM. So we're just going to create a certificate in this case, and it is going to be an EICR, because that's what we've done. We can select all the client and company details and stuff, but we're going to ignore that just for the minute and create a nice blank testing inspection sheet. So you can see here with the OM software, you're faced with the usual, where you can insert your client address, the purpose of carrying out of the report, the occupier's address where it took place, the type of premises, estimated age, any prior inspection numbers, so your certificate reference numbers, the limitations, so the extent what you're covering and anything that you're limiting. So as I said during the course of recording this video, we are excluding the fire alarm system and the emergency light duration testing. So if you want to note that in there, you can. But equally, if there's any other aspects of testing you're not able to do due to access or restrictions in the way the building's operated, this is the place to insert all of that. And we could make note of an issue around our installation resistance testing and the approach we're taking as regards that as well. But there's also space on the actual test sheets where you can make note of that as well. So you can make an observation on the general condition of the installation. So if you want to surmise what you've seen into a paragraph, the more information the better, as long as you're setting out exactly what you have been doing. Then got the observations. So as I will mention at the end of this video, when you see later on, we're actually going to let the viewers have a go at coding this. So if you've seen some things through the course of this video and you want to apply a code, please do so and we'll revisit it on a later video when everybody's had a chance. On the page 3, you're kind of setting out what the arrangements are of your installation. So you put when you're next going to recommend it's going to be inspected, set a date for that, put all of your information into the certificate, and then you've got your earthing arrangements. So as I said, this is a TNS, but as we know, lots of the DNOs are now saying to assume TNCS unless you're otherwise absolutely certain it is or it isn't. But you can record here if you've got a 3-phase system, the voltage requirements, what the UO and U are. So it's important to understand the differentiation between those, especially if you're working in a 3-phase install but at a single-phase board. And you've got all of that information where you can pop that in there. So if we was to make the assumption on this, we'll say we know it's a TNS. It's a private supply on the property, and we know that that's the case. We can then enter our voltages and frequency. And the interesting aspect of stuff is to do with the prospective fault current. And if you remember during the course of the video, I took a ZDB measurement. So this is at the actual distribution board. And that's not the same thing as what you would be entering in these locations. That's the prospective fault current and supply characteristics of the earthing arrangement at your source. So you need to be taking these measurements at that location. And we haven't done that through the course of this video, so I'm not going to insert them here. And I'll show you where you record the information that we did actually gather. But you do the same thing, take your ZE measurement, record that in there. That's your impedance value. So say it's 0.3, for example. You could pop that in there. If you've got a prospective fault current of a kiloamp, that goes in there. And then the protective device that's applicable to your supply, again, you would pop that into there. So if you've got 1361 fuses, for example, that are rated to 100 amps, or if you've got 200, 400 amp fuses and so forth, note what they are, state the short circuit capacity of them, and they all go into there. And then confirm the supply polarity. So then you've got your inspection schedule, and that relates more to the wider installation. And again, if we found an issue with anything, so we mentioned about that plastic consumer unit near an escape to the room, if we're going to mention that, we can flag that up through this software and then apportion a code to it, which will automatically link back into the actual observations area. So if we have a look at that, we'll just use an example. Let's see what we can find. So we've got the consumer unit, and it says here, condition of the enclosure in terms of its fire rating, and the general outcome. So if we click on this box, we can choose a code if we want to say C3, for example. We haven't got any circuits listed for the minute because we've not filled out the test sheet, but eventually we will have, and we can come back and choose the circuit arrangement for that. We've got the outcome circuits, so we can make sure we detail those as well. Any comments we want to make that would transfer through to the observations. So if we want to say an IP plastic consumer unit located at the exit point to the premises, and then state the regulation that applies to that in terms of its non-compliance and the reason that you're suggesting it's a recommendation for improvement. I'm not saying that's what we are going to do in this case, I'm just doing that as an example. So we'll return that back to just a pass. We'll leave it as a pass there for the minute. And that should clear that code. and you get your outcome there. So again, you can pass all empties if you want to very quickly fill everything in super fast and then work your way through and add in any of the non-conformities that you've seen. Really simple and fast way to fill out your inspection schedule. So with the distribution boards then, this is relatively simple for us because we've just got the one board. So we can insert our board, we can call it DB2 because we are aware it is a subboard on the installation, and we can put that it's in building. It's building 11, I think that was. It's a single phase supply. It's just a two-way board. If you want, you can default the cable in system as well, so we can know that the PVC cables, it'll fill in automatically on the test schedule. If you do that, if you've got a bigger board, that's really useful. And the reference method, we will just say that it's clip direct because it's in the wall, clip direct. And we can choose a size of conductor. Again, if you've got a bigger installation, it's useful because you can lay all that out in terms of your selection of cable type when you're running through the circuits. And again, we can choose our 60898 type Bs. If we want, we can specify a rating and it'll pre-populate all of that into the sheet. As you can see here, we've now got two circuits and it's populated that information in, and we need to make sure we're adjusting this as we move forward. So if we look at the circuit arrangement, we had our sockets and then our lights from memory. I may have to just quickly check back into the video and adjust that actually, because I'm now questioning myself in which order they were actually in, especially as I got them mixed up and had to swap them back over. So just bear with me 1 sec. I'll just scoot across and have a look at that and come back to you in 1 minute. Okay, so I was correct. That is the order it's in. And we can see there's no observations or anything on these for now, but as I was saying, they will link through. So if we was to click on these, you can make an observation and it will add that in straight from here as well, which is really useful. The number of points served on the sockets, I think we had 4, didn't we? There's one in the consumer unit, one with the USB sockets, one for the TV, one for the kettle. And the lights, we had the emergency light, the light as we came in the door, the one above the bed, 2 lamps at the side of the bed, 2 lights in the bathroom, which gives us 7, and then we had the fan, which is 8 fittings, unless I've missed something there. We need to adjust this cable because this was just 1 mil, so we can adjust that off there as well and pop in 2 times here just so we know that that is a ring final. And these are 0.4 second disconnection times, and you'll see it'll automatically populate the ZS value over here. However, for the lights, we need to change this down because it's only a 6 amp MCB and there is no RCDs at play with any of this. So we can NA these off as we go through. You can leave them blank and just do an NA all blank fields at the end, but we'll just quickly do these because it doesn't take a minute. And the rating, obviously, that's NA as well. Pop that in there too. Now, if you had RCDs, if it was a global RCD looking after these 2 circuits, you would list what it is in there. So if it was a 61008, for example, it was type AC, it's 30 milliamp, and it was 63 amp rated, for example. Or if your RCBOs, detail that in there as well. Now our ring final, so our little R1, which is the live continuity, we got 0.33, if you remember, on that one. So we've got 0.33. The neutral was a little bit higher at 0.35. And our R2, which is the CPC, was 0.56. So if we play around with some maths on that, we know that 0.35 times 1.67 should something like equal 0.56. So I'll just grab a calculator and we'll do that now while we're on the recording, just to double check. And you can see I'm not fixing this because you saw me retake the values, and we'll talk through the maths now. So if we times that by 1.67, it's coming out at 0.5511, which is pretty close. So that plays out as accurate, and it gives you a good feeling that the figures you're recording are kind of playing out in what the maths are telling you it should do, which is nice. Now the R1, R2 measurement was 0.22. So if we add 0.56 to the 0.35, so 0.56 plus 0.35, we're coming out at 0.91. If we then divide that by 4, that should give us the value of R1, R2, and it's coming out at 0.2275. So again, the maths there are helping us out to show that that's correct. Now with the lighting circuit, there is no ring continuity or parallel cables to measure, so it is just the R1, R2, and that was 0.67 as a maximum. So we've got that in there. Now the insulation resistance values, the live to live, so that's between your line and neutrals. Obviously we had a 0 value on those, but it is to do with the equipment that's connected into circuit. We had issues with the USB socket and also with the lights that are obviously still in there and the circuit boards and so forth. So it's really difficult on an existing installation with lots of equipment connected to disconnect all of that and take a measurement. So you can either make a limitation of it and you can record the value of 0 if you want, because that is effectively what we did record, but we know that there's an acceptable reason for that to be the case. I'll just pop 0 in here for the minute because why not, and we'll note it. Now the live earth values, that's the line and neutrals together to earth. So if you've done them as a combined or you've done them separately, you can record that data into this box. And with the socket circuit, we know we were off the scale at 499 plus. And this is at 500 volts, which will, 250 volts, which we'll put in there at the minute. And this one was 23 megohms, roughly speaking. And our test voltage was 250 volts. Now, we could, during the course of testing, have bumped up to potentially 500 volts and done live and neutral together to earth. However, because the lighting circuit kind of had a connection into earth, it's still a risky game doing that, I would say. So it's one to be very careful with when you are on EICRs, and you can often justify a lower test voltage as long as you're clear in the reasons why you've taken that approach. So the maximum measured ZS values on the actual testing, we'll pop those in here. And on the socket circuit, that was coming out at 0.66. So again, with the maths, right at the start of this video, I took a ZdB, which was 0.43. We'll enter that into this certificate in a minute. And roughly speaking, if we add, excuse me, that 0.43 to our R1, R2 value of 0.22, it isn't far away. So again, the maths and the testing are kind of verifying each other, which gives you confidence that at every stage you've kind of recorded the right value and you've got an explanation for that. And the importance of the ZS at the end is obviously we've been interfering with a lot of these connections. We're taking a live measurement through the actual system during working conditions to a point, although there's no load. So if there's any issues within the MCBs or any of the switchgear leading up to this point of work, if you like, we obviously know there's distribution circuits involved leading up to here. You know, the earth path's intact and measuring out as it should. And again, with the lighting, we were very consistent again. So we had the 0.67 on our R1, R2, and looking at the maths, it should come in at about 1.1-ish. It was actually 1.12. So it's very close, and that's good to see. So there was no RCDs, no AFDDs, so these can just be NA'd. And the remarks again, so in here you can make a note of your equipment that's causing you an issue with the insulation resistance testing. So you can say there's electronics connected in circuit. So you've dropped down to 250 volts test value to limit any damage to them. And you've broken it down on a circuit by circuit basis to try and show where those are having more of an impact than not. So with that USB socket, for example, on the socket circuit, obviously there's a path line to neutral through whatever it is in there that makes the USB magic operate. However, there isn't a real path back through to earth. So the filtering on that, the earth filters within that USB socket were holding up strong enough for the duration of the IR test for that not to be a problem. However, within the lighting circuit, where there's a bit more electronics, so you've got that emergency light, which has got a PCB in it, and there's the fan as well that's got a PCB in there, along with some of the lamps that would be LED with drivers and such. There is always leakage back to earth just naturally in the way those are set up at an electronics level. So you're going to see a bit of a lower value on your live to earth paths. It should never be too low, because you can always have that problem when the circuit's in operation that your RCDs are going to operate. But there is a path there, and it's understanding why it's there and being able to explain it and reference that and know that you're still in compliance with the regulations as a whole. Now, obviously, you've got that maximum 2 mega ohm limit on the installation as a whole, so you need to factor in if there's lots of these things pulling that down through a number of circuits, you can end up developing a problem, because when they are all linked together in the consumer unit distribution board linked together, that cumulative effect can drop your global value. So it's important you're mindful of that and checking it as well. But we'll have a little look now at entering the distribution board details. So if we press on details for this board, we can see a bit more about it. So we can note where it's supplied from, the number of phases and voltages. So we can make all of that in there, the overcurrent protective device for the circuit as well. And again, I couldn't show you this on the video, but whatever it may be, if it was 60898 rated at 50 amps, you pop that in there. If it's supplied from DB1, which is 3-phase and 400 volts in there, if there's any RCDs, you pop that in there. And now we can put in the ZS at this distribution board. So we know from our measurement it was 0.43. So that's our ZSDB. And again, as we said during the course of the video, you do that with all of your parallel earths in place, because we're looking for that lowest possible value at this stage with the system in operation as it is with bonds. And you can't realistically be disconnecting all the bonds off to the wider install anyway for you to gather that measurement. So the IPF at the distribution board, this is your fault current. And we had the PSC, which is the short circuit line to neutral of 329 amps, but the PFC, which is the fault current through the earth path, was 406. And that's kind of explained with the extra earthing conductor in the board and the fact it's a TNS earthing arrangement, whatever the DNO tell us to assume as regards TNCS. So we're recording the 406, sorry, it'll be 0.46 because that's Ka in this box. And again, there's no RCD. You can confirm the supply polarity. If there's phase sequence, you can confirm it in there. And then you're making a note of the test instruments you use, so your multifunction tester serial number. Pop that in there. If there's any surge protection devices, you can pop that in there. Details of any circuits or installed equipment that's vulnerable to damage. Now, this is where you would itemize the socket and lighting circuits, have equipment connected in circuits such as USB sockets, such as the extractor fans, the emergency lights, and LED lighting with drivers and controls that are potentially going to be receiving damage through doing insulation resistance testing at up to 500 volts, and also affecting the measurements recorded between live conductors or something to that effect. If there's any other cable types that aren't listed in the cable selection options, so if you've got some FP100, for example, that isn't listed in the chart, you can pop that in there and then sign your life away and date it, so it's all in on that bit there. So that's all of the data that we've recorded from out doing the testing, and it kind of verifies the results throughout the course of doing it, which is nice. I hope that's kind of explained a little bit about how you do go approaching filling in a test sheet. It's quite basic, really. You gather the data by running through the test process. If you want, you can fill it in as you go. It's often handy to verify your measurements while you're doing it if you're unsure. I knew while I was recording these that the maths looked like they were kind of playing out through the values I was seeing, but when you're not quite so experienced and just starting out on your testing journey, it's well worth checking that as you go, because you might have put a probe in the wrong place, had something not quite connect correctly, and you may just need to repeat the process and double check the values you're getting are actually accurate, and then trying to find out the reason for them maybe not being quite as expected through the course of your inspection and test. So we'll have a little chat at the end of this video and close this one up. That is the electrical OM system in terms of recording the data. And as I've shown before, you can build this up in a design and have all of this magically brought through into your certificate ready for filling in the test data as well. It is an absolutely awesome bit of software, and there's a link in the description for anyone who wants to go off and try a free 14-day trial.
So I hope you found that interesting, having a look through the EICR. You can see the test results came out as we would kind of expect based on what is installed. The observations in terms of any physical damage to equipment wasn't really anything at play. There is some questions around coding on this plastic consumer unit and on the potential issues around the supply arrangement to this particular area and no RCD protection. So if you've got an opinion on that, drop them in the comments below, and in a couple of videos time we'll come back to it, and if enough people have got involved, have a discussion around the coding before I give my opinion on it and show you how this report actually panned out in full. I thought that might be interesting to see what the community following along from my YouTube channel actually thinks. So get involved in the comments, say what codes you would apply. If you've spotted anything else that I may not have mentioned through the course of this video, drop that in as well. we'll see what the Mind Hive of YouTube can come up with in terms of coding and a report on this particular EICR. Thank you very much for watching. If you've not subscribed already, please do so. Most people who watch these videos aren't subscribed, and it makes a big difference to the channel's growth and more people who like and subscribe to the videos. So if you have enjoyed it, give it a thumbs up, click the bell, and hopefully I'll see you on the next one.